In this video, we're going to go over some practice problems for single replacement reactions. So this is one of the assignments that I'm going to be giving you. And what you're going to do is you are going to predict the products of the single replacement reactions and then write the balanced half reactions for that. Now, in order to do this, you need to tell me, first you need to figure out if the reaction happens or not. And we do that by going to table J. So the way it works is higher metals replace lower metals on table J. So we look for the metal, Li and Na. Li is all the way at the top, so Li is going to replace anything, and Na is below it, so therefore this reaction happens, and Li is going to go into the compound, Na is going to come out of the compound. And so what do we get? We get Na alone, and then we get Li with Br. Now before we go any further, we're going to have to assign oxidation states. When they're alone, they're always 0. So when they're in the element form, Br is group 1. So we're going to assume that Br, not group 1, I'm sorry, it's the halogens, which is group 17. We're going to assume that Br is going to be just like F and that they're going to be -1. So that's actually something that's going to be true for this whole sheet. Anytime you deal with a halogen, we're going to assume it's -1. And then we assign the oxidation states for the metal, in this case, +1 in both instances. Now we've got our numbers. So the next thing you're going to do is you're going to do your half reactions. So the way we do that is by figuring out which two changed. The obvious answer is going to be the metals. So lithium went from 0 to +1. So it lost electrons, it was oxidation, and it lost 1 electron specifically. Now, once I know that, I know what sodium did because it's impossible for it to do anything else. Sodium must be GER or reduction because you can't have loss without gain. In other words, when one element loses an electron, a new element has to gain it. So there always has to be both in a redox reaction, which single replacements are in that category. So you're always going to have both. So once I know one, the other one's guaranteed to be the opposite. And so this one, sodium gains 1 electron. So sodium was reduction, so that means it's going to be here. So I'm going to draw it out. And the way I do that is by ignoring everything in the reaction that isn't sodium. So sodium gained an electron, so there's my Na+1, plus an electron turned into Na0. Then for lithium, Li0 turned into Li+1 by losing an electron. And then the last step would be to balance them using coefficients. And again, to balance them, these would just be 1 and 1. I am going to change one thing. I was going to have you balance the chemical reactions. Actually, yeah, I'm going to have you balance the chemical reactions too. So there wasn't a space for them here. But balancing this is actually pretty easy. They're all ones. Now, be aware, your balancing coefficients don't always match up to your half reaction coefficients, and there's a reason for that. The reason is that when we do our half reactions, we do them for a single atom or ion, whereas in the chemical reaction, it's balancing the entire compounds that sometimes have multiple atoms in them. So for number 1, it worked, but when we get to a problem like probably number 4, it's the balancing coefficients for the reaction are not going to line up to be the exact same balancing coefficients. Actually, I think they do in number 4 as well, but sometimes they don't, okay? And so that's something too important. Number 6, they definitely don't. So your balancing coefficients aren't the same all the time. In simple reactions, they will be, but as the reactions get a little bit more complicated, they won't be. So just be aware of that. And again, the reason is because we're only drawing the most simple form of the half reaction. If we were drawing true half reactions, which are more complicated, then they would match up every time, but we're not. So now I'm going to do... We'll jump to number 3 because I want to show you what happens when on number 3 is a different scenario. So then the question is, will Na replace Li? Well, we just answered it. We know that Li is above Na, so the reverse won't happen under natural circumstances. So in no reaction. So for number 3, guess what? That's all I needed to do for number 3. It's done. Once you know there's no reaction, then you can't do half reactions because there's no reaction. And then the last question would be, some people ask this, spontaneous versus non. It's real easy. The reactions that happen based off table J, those are always spontaneous. The only ones that would be non-spontaneous would be like number 3. If a scientist forced this reaction to happen by hooking it up to an electrolytic cell, we could then force the non-spontaneous reaction to occur, but in nature, that will never happen. So it's spontaneous are the only ones that occur in nature. In a lab, we can force non-spontaneous to happen, and that's it. So just so you're aware, there are 3 reactions on this sheet, front and back, that will have a no reaction with it. I gave you one of them, so that means there's 2 more out of this entire sheet that will have no reaction, and then the other 9 out of 12 will definitely cause reactions.